Okay, so I'm going to start this video with talking about where we left on Friday, I believe. So we had this idea that if you collect data from a distribution and you do a histogram, then if the histogram is going to pass some tests, which we're not going to talk a lot about in this class, but if there's pass some tests to decide if it's approximately normal or close to being normal enough to assume it's a normal distribution, then what we do is you calculate the mean and the standard deviation of your distribution, and you use that into the formula that we saw for the normal curve. Right? Once you put that in the formula for the normal curve, then this curve will follow this one, and which will be very close to the matching, very close to the one that you have for your histogram. So from now on, every excuse me, every calculation or question you want to talk about the data, which is usually it's like, okay, you have this population, what's the probability that you select somebody at random and that you have less than this value or more than that value or right between two values, then instead of using the data, you just talk about the areas under the normal curve. We talked a little bit about that here when we said about this giraffe problem, right? So the area to the left of 2100 under this example was the proportion of giraffes that weigh 2100 pounds or less. Or you can assume another way to think about this is like you're saying, if you select a giraffe at random, what's the probability that that giraffe's weight is less than 2100? Now, something here to clarify is that a little bit, and sometimes this comes up, is that here the less than or equal or less than is not important, because what you're going to be thinking is this area, and if you include 2100, including the line here, if you exclude it, this would be like a dotted line, but you're not changing the area to the left, right? That's what's important. So the less than or less than or equal for this way of thinking is not important. Okay, so we should have a way to calculate areas to the left or to the right or between two numbers under any normal curve, and we are in 2019 and we have technology to do that. It's still important to know how this was done in the past, because some of those things still carry forward. For instance, what we do in section 5.3, there's no way around something that I'll tell you in a few minutes. So you need to know what is the logic of what's going on here. So the basic picture, here explain it with the words, but I think the better idea is the next slide. So let me move on to the few slides. I don't want this slide. I'm going to move all the way over here. We'll go back to the slide in a minute. So this is 5.2. I talk about 5.1 and 5.2 together because in the book they make a distinction, because you need to find a technique for 5.1, and then once you master that one, they introduce you what to do in 5.2. Basically, 5.1 is working it under the normal curve, standard normal curve, which is the one on the left, sorry, the one on the right in this picture, the one that has mean 0 and standard deviation 1. So 5.1 does everything on the standard normal curve. So find areas to the left of a value, to the right of a value, between two values under this standard normal curve. Okay. Now, in 5.2, we say, okay, what if you have a different normal distribution with a different mean and different standard deviation? Well, the important thing is this. For example, this example that's pictured here, taken from the book. If you want to find the area to the left of, say, you have a normal distribution that has mean 500 and standard deviation 600. If you want to find the area to the left of 600 on this curve, that's exactly the same than finding the area to the left of 1 under this curve, the one on the right. Why? Because 1 is exactly one standard deviation to the left from the mean here. So all you care about is finding the area to the left under a normal curve that has to the left of one standard deviation to the right of the mean. And that's exactly what this is on this side as well. Right here, you're also saying what's the area to the left of the curve under a normal curve from one standard deviation away from the mean to the right. Right. So this is the same area under this curve, x less than 500, that under this curve, z less than 1. This is the basic idea of why, how you can use the standard normal curve, which is this one, the one that has mean 0 and standard deviation 1, to calculate any other, the area under the curve of any other normal distribution. All you have to do is find on this general one, you find the z-score, okay? And once you find the z-score, then you're really just thinking about it on this curve, and you find the area to the left or the right of the z-scores. The way the notation here is important, when we use x, just as this is saying like, this is writing like, what is the probability of x less than 500. There's a probability that z is less than 1. Oh, this is wrong. This should be less than 600, right, on this side. The probability that x is less than 600 on this side is the same as the probability of z being less than 1. Now, why we use these on this guy is because it's z-scores. Okay, so get used to that. Whenever we talk about z-scores, it's the same as thinking of the values on the standard number curve, which is the one that has mean 0 and standard deviation 1. Okay, let me see if I need to go back to tell you what's going on here. So when you find the area to enter the standard normal curve, there was only one way to do this, I don't know, 20, 30 years ago. It was with these tables. And that's the tables that I referred to at the beginning of the quarter. At the end of their book, they have these tables. And it's always area to the left. So if you want to find the probability, or what is the area to the left of a z-score of 1.68, this means what is the area to the left of 1.68 under normal curve that has a mean 0 and standard deviation 1. So you go and you have to go to these tables, okay? And so this table is, you go to the column for the z values, 1.6, and this is 1.60, 1.61, 1.62, and 1.68 is this value. So it'd be 0.9535, okay? So these are tables like, I don't know, if you think about, this is not totally weird. Some of us have, I don't know, a uncle or a grandparent who was an engineer, and when they did any trig calculations in the 40s or the 50s, they would have these big books where they would look for tables of values for sine of 65.3, sine of 65.36. So what you did, somebody calculated these numbers, and then you print them and you give it away. Now, basically, your calculator has these in internal memory, and they can find them for you, right? But this is the way it does. But the important thing to understand is that it's always area to the left. If you want to find the area to the right of this value, well, it would be the difference between this and 1, right? It would be 1 minus 9535, correct? Okay, and then we have to figure out what to do if you find the area, if you wanted to find the area between two values, right? And if you want to find the area between two values in the normal curve, then you have to subtract the two values in the normal curve, in the table for the normal curve. Okay, so this is a picture of what I'm talking about. It's a little bit funky, but it's the standard normal curve, that one that has mean 0, and then it puts standard deviation 1, but it's around here. And this is 1.68. So to the left of 1.68, this area is 0.9535. Okay? Okay. Now, what if I want to find the area on the standard curve that lies to the left of 2.53? Using the table, I have a link here to open the table. I'm not going to open the table. I don't have it, so I can't open it. But I want to find the area to the left of 7253. So in the calculator, there's no way to do this. So there's no infinity symbol, right? You want to find the area, like in this point, this area, remember that this is an asymptote on this side. It never really touches it. So I want to find the area from negative infinity to 1.68. There's no infinity in the calculator. So the way we do this is we put the calculator to do the value between negative m and 2.53, where m is a very large number. Now, what does it mean, very large number? Well, I mean, we can be picky and say, well, let's use 9 times 10 to the 99, which is the biggest number your calculator can type. And we can do this. So so you want to find the area in the interval negative 9 times 10 to the 99 all the way to 2.53. And so this is the command you do in your calculator. So I have the calculator right here. So let's do it. It's right here. So where's that button? We're going to start using this one. So the second of the variables button says distributions. So you press here, and you scroll down to normal CDF. That's normal cumulative distribution function. And it already has it right there. It already has a negative 1. That's the lowest it could be. By default, mine has a negative 1 times 10 to the 99. My upper is, I want to use 2.53. And see, this is an important thing, that my calculator is already asking me for a mean and a standard deviation. So I can change that, right? It doesn't have to be the standard normal curve. I can type a different mean and different standard deviation. But right now we're in section 5.1, so let's leave it like that. Now remember, if your calculator doesn't have a menu like this, I'm going to put the paste button. All this really does is really fill this is the command that I did, right? So it just copies it here, and this is the way you write it. So if I write here, for example, if I write negative 99 here, it really doesn't matter. If I want you to see the whole thing. Oh, I erased the wrong thing. Shoot, where am I? Oh, sorry, I erased it. Okay, and let me do it again. So second distributions, number 2, normal CDF. I have it in my memory, so I can go to paste, enter, and I press enter again. So that's my number. Yeah, it's 994926853. Now I want to show you something. If I do, if your calculator doesn't have the menu thing, you type the normal CDF and you will have this. Okay, let me erase. I think I can scroll back and erase these guys. Yeah. So a couple things. If I leave it like this, I have 2.53. That really is all you have to enter into your calculator. If you don't have this menu, the normal CDF button will give you this, right? So if I type here, does it work? This is, you can't see the normal CDF, but that's what it says, right? So if you type this and I don't put a mean and a standard deviation, so if I close it and after just giving it 2 inputs, it's going to read, that's my left bound, that's my right, and by default it will use mean 0 and standard deviation 1. So if I click this, I get the exact same result. Okay, so you don't, the term 0 and 1 are really optional, and you only really need to use them where you're not going to be using the standard number curve, the one that has mean 0 and standard deviation 1. So the other thing I want to show you is that I really didn't need to put this very, very tiny number. I'm doing, this is the wrong picture, but let me show you what's going on. I'm in a 2.53, so it's way over here, right? Another station to the left, so over here. And if I need error to the left of that. So if I stop at negative, I'm way over here. If I stop at negative 100 or negative 20 or negative 5, the area I'm leaving to the left of that is not going to show up in my picture. So if I make this, if I do second distributions, normal CDF, number 2, and all I do is say, I'm going to put from, let's say from negative 10. Yeah, why is that? Because I'm using, think of this, I'm using standard deviation 1. So this means I'm at least 10 standard deviations to the left of the mean. It's way, way too small. Yeah, I see no difference at all. Okay, so this number on the left bound, it could be any number, any big, large number. You have to use a criteria to know how big, right? Like if you're examples where the mean is 10,000 and the standard deviation is 5,000, or the mean is 0 and the standard deviation is 5,000. So then you have to move to the left a lot more, right? It really matters you have to be to the left in terms of standard deviations. If you're 5 or 6 standard deviations to the left, it's not going to make any difference. When will this make a difference here? If I put a negative 1, that would make a difference, right? Because I'm only 1 standard deviation to the left of the mean. So I hope you understand that this is the left bound is not that important for now, as long as it's a very big number.